Hello, welcome to the General Chemistry 1 Refresher course. My name is Desiree Morales. I'm one of the academic peer coaches in the Palo Alto College STEM Center. Today I'd like to introduce you to some topics that are covered in the General Chemistry 1 or Chem 1411 course. Some of the concepts I'm covering here will not be too in-depth, but I'm just trying to give you an overall picture of how the course will be. I'd also like to make a disclaimer that one, if you struggled with college algebra or if you haven't taken the course in a while, please check out the College Algebra Refresher course, as a lot of the sort of calculations and foundations of General Chemistry 1 build off of that course, and you'll be utilizing a lot of those type of math skills. The second disclaimer I like to make is that not everything that is seen in General Chemistry 1 course I am going to be covering here. That is because the course is a very dense class. You're going to be covering a lot of information, but it's more so of calculations and repetition as far as being able to nail those equations down. Here are some basic terms and concepts. I'm not going to go ahead and read off of all of these, but I'm going to go ahead and explain to you a few key ones that we'll see in this presentation. You are more than free to go ahead and screenshot these for your reference later on, as well as your professor will most likely provide you their own definitions. Looking first, we'll look at the three key parts of the structure of an atom, which is the proton and neutron, which are centralized in the nucleus. The nucleus is in the center of the atom. Protons have a positive charge, neutrons have a neutral charge, electrons have a negative charge. And these electrons are moving around the nucleus, so they're kind of circling around while the protons and the neutrons sort of hang out in the nucleus. Moving on to chemical reactions, we'll sort of introduce you to sort of what a chemical reaction is, as well as being able to balance a chemical equation. A chemical reaction is the process of when compounds are formed or broken. Let's go over a quick little easy example. Let's go say sodium chloride or table salts, so NaCl. So Na, that's your sodium. Cl is your chlorine. Whenever those two come together, they form a compound known as sodium chloride. That is also known as table salts, so that is like sort of forming a compound. And so the sodium and the chlorine will be your reactants. They're going to be on the left side of the chemical equation, whereas them two together as a compound are your product, because you're forming the product, you're forming the compound. The next concept that a lot of students get confused or mixed up is the difference between a covalent bond and an ionic bond. A covalent bond is just the sharing of one or more pair of electrons, whereas an ionic bond transfers one or more electrons. You can think of this covalent bond as the covalent, so they're kind of cooperating together, so they're like cooperating friends. They're sharing their snack, they're sharing their things. Whereas an ionic bond transfer, one of them is going to be more electronegative, which I will go into what that means later, and they're going to be a little bit more selfish. So you can think of like ionic bond, I want to take those electrons. It's still going to form a bond, however, it's going to be more of a transfer of the electrons rather than sharing. Another key concept that you will see more in Gen Chem 2, so if you're watching this video to refresh yourself from taking Gen Chem 1, you will be going in more depth of acids and bases, as well as buffers. So just to refresh yourself of what that is acids have a higher concentration of hydrogen ions or hydronium ions, whereas bases have a higher concentration of OH ions or hydroxide ions. And this buffer has weak acids or base that react with strong acids or base to prevent changes in the pH from going up or down. They kind of keep it in that sweet spot. Moving on to another example of a chemical reaction, Let's take another easy example. Here we have the chemical reaction of how to make water, or H2O. H2, because I have two hydrogen atoms, and one O, because I have one oxygen. What's going to happen is that because oxygen is so electronegative, or wants more of those electrons, which hydrogen has on its outer shell, it's going to pull those two atoms together to form the covalent bond and form water. Going over the atomic structure, like I said previously, we have our protons and our neutrons, and this is how they look in a nucleus. So this whole thing right here is a nucleus. Protons have a positive charge, neutrons have a neutral charge, whereas electrons have this negative charge, and they're sort of circling around the nucleus of the atom. On a periodic table, which I will show you how to sort of interpret a periodic table later on, you'll see this sort of organization. So you'll see these central chemical symbol for the elements. So here we have carbon, C for carbon, and you'll be most likely given a periodic table during your exams and quizzes, so you don't have to memorize the periodic table, but it helps to be able to read and understand what you're looking at. So your mass number can either be on the top or bottom. You'll be able to tell as well in the periodic table is the number of protons, remember in the middle, plus the number of neutrons. And so here we have a neutral atom, so this is going to be number of protons, or my atomic number, that's always equal to each other. So you can see here another key thing to note is that the number of protons and the number of neutrons typically equal each other out. So 6 plus 6, because number of protons plus neutrons is going to get you to 12. In certain cases, we have isotopes. So isotopes is an atom with a different number of neutrons. So if I have a different number of neutrons, but a steady atomic number or number of protons, which doesn't change, if I'm changing the number of neutrons, that means that my mass number is going to change, right? So here you can see that I have more neutrons because now I went from 12 mass number to a 13 mass number. Let me give you an example so you can go ahead and sort of quiz yourself. So given that the atom I'm showing you here, fluorine, is neutral, meaning it's not an isotope, so it has the same number of neutrons as far as protons. That's kind of a hint. What is the mass number of fluorine? If you said about 18, you are correct. So you'll see on the periodic table the mass number typically in decimal form, and that's because the mass number typically varies and it's not an exact number. Going over the periodic table, let's go ahead and look at some of the periodic table trends. So ionization energy. Ionization energy sounds very complex, but whenever you break it down, it's actually pretty simple. So what it is the energy that is required to completely remove an electron from a gaseous atom or ion. So typically something like a noble gas, and noble gases you'll go over in Gen Chem 1 as well. So if I have a lower ionization energy, so it's going to take less energy for me to remove that electron, right? So if I'm trying to move it from a gas atom, like I said, it's going to take less energy to remove that valence electron. What about if I have a increased ionization energy? That means that the nucleus is pulling that electron back to the center of the atom, and it's going to be holding onto that electron because it really doesn't want to let it go. That means it's going to take more energy for me to release that electron. And because they're going to be requiring this energy, it's always going to be a positive value. So looking at your periodic table, your ionization energy is going to increase going up as well as going to the right. So you can kind of think of a trend going this way. Moving to electron affinity. Electron affinity is the enthalpy change, which you will also go over in Gen Chem 1, that results from the addition of an electron to a gaseous atom. What does that mean? So let's go ahead and look at an example here. So it's going to be if your electron affinity is positive, you're going to need energy. So need energy has to be positive, and I'm going to end up with energy over here. So that's going to be exothermic because I'm getting energy out, exo out, energy out. Whereas in endo, if I have a electron affinity that is negative, I'm going to need to put energy into the system in order to add that electron to the gaseous atom. So if I have a greater negative value, looking here, the more stable the anion is. And you'll also go over what an anion is later as well as I will kind of explain to you and introduce what that means. There are 3 different types of gaseous atoms that do not follow this trend. However, you don't really look too much into electron affinity in Gen Chem 1. And like I had stated, it can be positive or negative value as depending on if it's exothermic or endothermic. Looking at electronegativity, I kind of introduced this and mentioned it in the earlier example with oxygen being more electronegative than hydrogen. So electronegativity is how competitive is an atom for electrons in a bond. This is kind of, I always remember this one as some people are more competitive than others. For example, I'm a very competitive person, whereas some of my family members are not. So you can kind of think of the atoms as like these people. However, they're not actually people, but it's helpful to remember it that way. So if I have a higher electronegativity or a higher competitive nature for electrons, I'm going to have a greater ability to get electrons because I'm more competitive for the electron. This is important in polar and nonpolar molecules, which you saw earlier with water, which is a polar molecule, because the oxygen, because it's so electronegative, it's pulling those electrons to itself. It's kind of creating like a pull. These positively correlate with ionization energies. So if I have a higher ionization energy, I'm going to have a higher electronegativity. So when looking at the periodic table, the reason why oxygen was so electronegative versus hydrogen is because oxygen sits around here, this general area in the periodic table, whereas hydrogen sits all the way up here. So you can see the oxygen would be way more electronegative than hydrogen. And here is sort of an example of what I meant. So that oxygen is more electronegative. It's going to pull these hydrogens to this pole, make a polar molecule. You don't really go too much into metallic properties of General Chemistry 1, however, it depends on the professor that you are taking. But just to go over a key concept is that metals tend to lose electrons to form cations, whereas nonmetals tend to gain electrons. And that's because, like I said previously, remember, electrons are negatively charged. So if I'm losing that negative charge, I'm going to form a cation because cations have a positive charge. You can kind of remember cations as far as cats. Cats have paws, positive. Whereas nonmetals tend to gain electrons and they form better anions. So if I have a lower metallic character, I'm going to have a greater pull to the nucleus on the outer electrons. So it makes it harder for the atoms to lose the electrons because the electrons are kind of pulled into the center. So it's going to be harder to form cations because it's harder for me to lose the electrons. This is a summary of what I have kind of gone over. So ionization energy and electron affinity sort of go hand in hand together. Whereas atomic radius I didn't mention too much, which is not really looked too much into in Gen Chem 1, and as well as metallic character decreases this way. Let's look at some of the bonds that you see in Gen Chem 1. So a lot of times you're going to be having to characterize which one is a stronger bond. So the strongest bond is a covalent bond. And you can kind of remember this because we saw the sharing of the electrons. So if I'm sharing something, everything's sort of in harmony. It's a great time because there's that sort of equal attraction between the electrons. The next one is going to be the ionic bond. So it's going to be a transfer. It involves a cation and an anion, right? Because one of them is sort of losing that electron to the other. And so losing it makes it positive because the electron is negatively charged, forming the cation. And another one that's gaining the electron, or gaining that negative charge from the electron, is going to be an anion, which has a negative charge. The next strongest bond is a hydrogen bond, which has like a dipole-dipole attraction. And so this dipole-dipole is sort of this attractive form between a hydrogen atom bonded to a very electronegative atom. So you can kind of think of water once again. Hydrogen bonds are very important in regards to not so much general chemistry, however they're very important in other classes such as general biology with the DNA structure, as well as in biochemistry if you ever do take that course. The next strongest bonds would be van der Waals, so it's kind of this attraction and repulsion between the atoms. It's kind of, they want to bond together, but they fluctuate a lot. So it's kind of like this on again, off again relationship between the two. The weakest one is dispersion forces, and that's because it's a temporary attraction. They're very hardly ever attracted to each other, and they sort of like are almost touching, and they kind of flee away from each other, from the electrons. Let's look at one example of stoichiometry. You're going to be doing a lot of this in General Chemistry 1, so let's go ahead and sort of give an example of this. So looking at my chemical equation up here, going from glucose over here to my products, if I have 2.5 moles of glucose, how many moles of CO2 or carbon dioxide are formed? Now you can kind of think of all of this as 1 mole, 2 mole, and 2 mole, because there's that sort of coefficient in front of it. So if I'm looking for 2.5 moles of glucose, and how many CO2 that will get me, well, I need to think of how many moles of glucose do I get per CO2. So per 2 moles of CO2, which you see here, it requires 1 mole of glucose. So I'm going to go ahead and kind of set it up this way, so it's that ratio between the two. And what you're going to do is multiply the 2.5 moles for every 2 moles of my carbon dioxide, and you'll get 5 moles of CO2. This may seem a little confusing right now, however you will have plenty of practice in General Chemistry 1, as well as more practice in General Chemistry 2. Looking at balancing equations, let's start with this example here. So the first step I always like to do is write out all of my reactants and all of my products on one side. And so when going to the next step of balancing equations, you're always going to leave hydrogen and especially oxygen for the end. And it's actually pretty convenient that they're both polyatomic here, or bonded to each other. We're going to go ahead and leave them like this. Now go ahead and count how many reactants and products you have on each side. So 1 barium, 2 chlorine, 1 sodium, 1 hydroxide. On the product side, we have 1 barium, 1 chlorine, 1 sodium, and 2 hydroxide. You can already see here that it's not completely balanced or equal on both sides. And the two that are not balanced are my chlorine and my hydroxide. So let's go ahead and fix that. The first way, like I said, you're going to leave this hydroxide for last. So let's go ahead and balance chlorine first. What you're going to do is go to the product side first. So if I have 2 chlorine on my reactant side, I need to get my chlorine on the product side to 2. However, I can't just put the 2 right in front of my chlorine because this is already a formed compound. I can't change it. Therefore, I had to put it directly in front of the compound. And like I said, with college algebra, you're kind of being distributing this 2 to both elements. So what we're going to do is multiply the sodium by 2 as well as the chlorine. And now what's going to happen is that you're going to be having this balance of the chlorine on both sides. However, now you have an unbalanced of sodium. Now you have 2 on the products, whereas you had 1 on the reactant side. So now we need to balance out sodium. So since I had 2 of the sodium over here, let's go ahead and fix the reactant side. Like I said, because this is already a formed compound, you can't just slap it in the middle between the elements. Therefore, the 2 has to go in front of this whole compound. So I'm making my sodium happy because now we have 2, so that's balanced out. And it's convenient as well because now this 2 not only gets distributed to the sodium, it also gets distributed to the hydroxide. And so now everything works out, and now you have a balanced out equation. Looking at some of the physical and chemical changes, I'd like to go over this because you're introduced to it in General Chemistry 1 a little bit. However, this is a very, very high yield and key concept of General Chemistry 2. And you're going to be doing a lot of equations and calculations with this concept. And for those type of calculations and equations, it's very, makes it a lot easier to understand what's going on as far as the background in order to understand why you're doing that calculation. So let's look at an example here. Here we have my system and my surroundings. So we have 2 different systems. In this system, we have an endothermic sort of system or reaction here. Endothermic, so endothermic, that means I'm going to be putting heat in. Endo, you kind of think endo and in. I'm going to be putting heat in. So the change in heat is going to be greater than 0 because I'm adding heat. I'm adding heat to the system. So I'm pulling that heat and adding it to the system in order to get that reaction done. My surroundings are going to get cooler. And another key thing to remember is that you cannot just form or nor destroy energy. So that energy is going to be transferred to the system or to the surroundings. Looking at the exothermic reaction or example here, in this one, I'm going to be releasing heat out or exiting heat out. So my system is going to get cooler because I'm releasing that heat. So my delta H is going to be less than 0 because I'm getting rid of the heat. Therefore, in consequence, my surroundings are going to get warmer. Some examples are when solid dry ice vaporizes, the carbon dioxide molecules are going to absorb that energy. Another example is when liquid water becomes ice, energy is released. And we'll kind of go over more examples in the next slide. You can go ahead and pause the video or screenshot these, or you can go ahead and follow me along. I'm going to be going over each one and sort of explaining what why is exothermic or endothermic. So I'd like for you to label each of the following processes as exothermic or endothermic. So what about water boiling? Do you think that that's going to be an endothermic or exothermic reaction or process? If you said endothermic, you are correct. That's because if I'm placing a pot of water in the stove and I'm giving it heat to get the water to boil, I'm adding heat and energy, and so the process is going to be endothermic. So I'm trying to get that water to boil, I'm adding heat to my system. What about gasoline burning? If you said exothermic, you are correct. So whenever you burn something, It feels hot to you because you're giving off the heat into the surrounding. It's burning, it's releasing that heat. What about ice forming on a pond? If you said exothermic, you are also correct. So think of ice forming in a freezer instead. You put water in the freezer in the ice cube tray or whatever you have, and it's taking the heat out of the water, right? Because you're trying to form ice, which is cold. So you're trying to get the heat out of the water in order to get it to freeze. And so it's because the heat is being pulled out of the water, it's exothermic because the heat is leaving. You may also be introduced to states of matter, as well as more of a phase diagram in regards to solids, liquids, and gases. I'm not going to go over too much of the slide. You can go ahead and screenshot and come to me if you have any questions. Like I mentioned in the beginning with my disclaimer, there are topics that you may encounter in General Chemistry 1 that I did not discuss here. You'll be going over nomenclature for sure, which is just being able to name the compounds from looking at them. You'll have plenty of practice with this with the professors here at Palo Alto College or any of the Alamo colleges. You will also be going over gas laws and kinetics. This is a lot of definitions and applying those definitions and calculations to what has been given to you. And you'll have plenty of practice with those as well. Because it's not an easy concept to show it to you in a presentation, you are also going to be doing a conversion of units. This is a fairly easy concept, and with more practice, you'll be able to nail it down. But this is very, very important for Gen Chem 1 as well as Gen Chem 2. Typically, you'll be given a exam question, and you definitely need to focus on the units that you're given. A lot of the times the question's easy, it's just a matter of converting your units and then being able to plug it into the equation in order to get your answer. Some tips for being successful in General Chemistry 1. I myself have taken General Chemistry 1 a while back ago here at Palo Alto College, and here are some tips that helped me succeed and get an A in the course. So what you need to do is practice, practice, practice. General Chemistry 1 is not so much a course where you memorize the concepts and are able to pass. You definitely need to practice the equations and calculations. You also need to start early and understand the concepts behind the equations because it makes it a lot easier to understand what you're doing. You can also use your professor as a resource in order to help guide you through the course as well as give you some encouragements. This is a very dense course, and it typically is a course where a lot of students feel that they cannot continue in their biology degree. I don't say this to scare you, but I say this in order for you to feel like you're not alone in this struggle. I myself struggled in General Chemistry 1, but definitely reach out to professors, and this is why we also have resources like the STEM Center, as well as the STEM Science Learning Center. So here are some resources. While we don't currently have anyone in the STEM Center that solely focuses on General Chemistry 1, we do have some in the Science Learning Center. However, we still do have resources and can help you to our best of our ability in the STEM Center. And if there is no one available, there are also YouTube videos. So a YouTuber that I like to use is Melissa Maribel. She has lots of different examples as well as quick videos explaining key concepts. With that, I'm going to conclude the presentation. If you have any questions, please reach out to me. And best of luck in General Chemistry 1.